Hello, I'm going to start a little video going over the ideas from section 3.4 so that in class tomorrow we can go over more homework problems instead of this. So this section, section 3.4 is about composition of functions, and what that means is we've talked about functions in many contexts already, and composition is one more way to combine functions, and essentially what it means is a chain of functions. I have one function that gives an output, and then a second function that takes that output, plugs it into a second function, and gives a final output. As an example that they have in the book, suppose that there's, over here there's a function t, the green function, the temperature function, that takes the input as a day, like the third day number 3 or day number 6 or day number 12, and figures out the temperature for that day. T of x is that function. And so t of x is that function. And then there's a second function that takes a temperature and it calculates some sort of cost. Maybe it's air conditioning or heating or whatever the cost would be. There's a cost function associated with that temperature, and that's the function c of t over here. And so if you have a composition function would do those two functions in a chain. And so it would give you this down below, you could have some composition function called f of x, which would be written as c parentheses t parentheses x, so c of t of x. And that would be the cost in terms of the days, the number of the day 6 or day 8. And you'd read that as c of t of x. And what that does is it combines the two functions into one and composes the two functions into one. And we'll give several examples how you do that in different ways. But first, I wanted to talk about other ways that you can combine functions that we've talked about in class. So it's a very simple concept, but the notation is sometimes a little bit weird for people. So this little notation here, let me back that up. So this notation here is the function f plus g applied at x. And f plus g, I can't spell, f plus g applied at x means the rule is you plug x into the function f and you plug x into the function g, and then you add those two outputs together to get the output for the overall rule. And you can do the same thing with addition, subtraction, multiplication, or division. And so this bottom one here would be f divided by g, is a new function called f divided by g. And if you plug in x to that, the rule is plug x into f and plug x into g and divide f of x divided by g of x. So it's a little abstract idea, but in context it's usually pretty straightforward. So let me give a couple examples with context. So if you had, say, a revenue function that tells you how much revenue you're going to bring in if you sell X units, and you also had a cost function that tells how much money it costs to produce X units, then you could define a profit function, which would be the revenue minus the cost. And so it would be the revenue minus the cost. But you could treat those as two separate functions. And so it's just a simple idea like that. But if you see this notation where it is f minus g, all in parentheses x, that means f minus g is the function. Another example you might have is something like this, where you have a rectangle that's expanding. So the width of the rectangle is increasing, let's say over here, and it, depending on time, it's increasing every minute. And the function it's 3 plus 2 times t after t minutes. And the length of the rectangle is 2 plus t after t minutes. So suppose it's a widening, lengthening rectangle. How does the area go as a function of time? Well, the area is the length times width, and so that would be the length at that time times the width at that time. And so you might have an expression that is the area function is L times W applied at t. Well, that's L at t times W at t. And once you evaluate or write down that expression, you can then do whatever you want with it to solve the particular problem, whether it's plug in a value for t, or multiply it out to get a nice expression, or solve when it's equal to some value, whatever you might want to do. But that's a way to represent the product of two functions. And so similarly, we have composition of two functions. And so the notation for it is this f circle g up here. F, it looks like the word fog, but it's f little circle g. And that means f composed with g of x. Or sometimes you'll say f of g of x. And it's important to notice that the second one in that term, the g, is the inside function, and f is the outside function. So when you're evaluating one of these, you plug x into the inside function first, and then you plug x into the output into the next function. So as an example, we've done these little diagrams for one-to-one functions and things like that. And so really you've got the first function that takes x and this function g, the inside, from the domain of g to the range of g, and you get some value w, which is equal to g of x. And then you've got the second function in this chain, which takes everything in the middle and sends it to the last version, to the last set, and your output is then y equals f of w. So that would be a two-step, two-function chain, a two-function composition, and you can write it as one function by having y equals f composed with g of x equals f of g of x, is how you'd say it. And that just means you follow those two steps, but in one step. So you go input x all the way over to this point here in one function instead of the two steps. So let me give some examples. So often these are thought about in very abstract terms, but it's important to think about them in terms of concrete terms. So here's an example they give in the book. Suppose you have two functions. F gives miles that can be driven in x hours. So the input for f is hours. You tell me I'm going to drive for x hours, and it'll tell me how many miles I can drive, whatever that function might be. And g is a function whose input is how many miles you're going to drive, and the output is how many gallons of gas it's going to take, whatever that function might represent. So then their question is, which of these compositions, f of g of y or g of f of x, which makes sense? And the way to look at that is thinking about them as a chain. So f takes, let me write it this way. F takes input of hours and gives out miles. G then takes an input of miles and gives out gallons. So that order, which would be x and then f of x, or and then g of x, works. So f would be the first function, the inside function, and g would be the second function, the outside function. But if you try to do it the other way, let's try it with purple here, and said you take in g, you take miles and convert to gallons to get g of x, and then you want to do f of g of x, that would take gallons, but you're supposed to plug in, f is supposed to have hours as an input, and so this all just doesn't work, right? You've outputted so many gallons, but f is supposed to take hours and do something with it, and so those don't line up. So in a real situation, you want to think about the units, what units are being converted to what units in each step, and make sure that it's just a sequence of conversions from hours to miles to gallons in this particular case. So they do ask in the handout, are there any situations where both f of g of y and g of f of x, both orders of the composition, would be meaningful? And the answer is, if it's just something like f of x is 3x plus 7, and g of x, or g of y, let's use a different variable, is y squared, then yeah, they both work. F of g of y is 3 times something plus 7, and I'm going to plug in y squared, so I get 3y squared plus 7. And conversely, g of f of x is going to be g of 3x plus 7, which is 3x plus 7 squared. So I can do either order, but they don't necessarily make sense. And when they make sense is when they say the units of the input and output have to be the same. So if one order, like we had before, goes hours to miles to gallons, you can't do those units out of order. But if the units are the same, if it was dollars to dollars and dollars to dollars, there's situations where that might make sense and you could put them in either order. But you have to have the inputs match the output, the units of the inputs match the units of the outputs. So let's think about ways that you could evaluate these, if we could do it quickly. There's a couple ways. If it's a composition based on a table like this, f of g of 1. Well, what's g of 1? In this table, I look at x equals 1, and the g says that's equal to 3. And so then I plug the 3 into f. What's f of 3? Well, I look at 3 and see what f tells me to do, and I get 3. So I can do this. It's just a two-step process. What about g of f of 4? Well, what's f of 4? I look at 4 and see what f tells me, so that's going to be 1. And what's g of 1? Well, I look at 1, and I follow the g, and I get 3 again in this case. So in both of these situations, I get 3, but that's just coincidence. So you can follow a table to give an output, and then take the output and plug it into the second function. So here's an example where they give you two functions, and they ask you to look at f of h of 1. And so one thing that I want to think about is sometimes it's good to think from the inside to the outside function. Like if you're evaluating, you can take 1 and figure out what h of 1 is, and that's going to be 3 times 1 plus 2, which is 5, and then do f of 5, and you get 5 squared minus 5, which is 25 minus 5, which is 20. You can do it inside out. Or you can kind of think about these sometimes outside first. That would be, what is f of something? So is something squared minus something. That's what the rule for f means. And I'm now plugging in h. And what's h? 3 times something plus 2. And 3 times something plus 2. And then I'm going to plug in, what am I plugging into h? I'm plugging into a 1. And I plug in a 1, and I plug in a 1. So you can think about this in terms of the form of the equation, the form of the function, something squared minus that something, and then plug into that. And then evaluate, and you're going to get 5 squared minus 5, which is 20. You'll get the same thing, but it's just, some contexts it's better to think about it outside in. Sometimes it's better to plug into the inside and work your way out. We'll play with both of those. So how do you calculate the domain of the composition? Well, it's all inputs that are in the domain of G, but the G of X also has to be in the domain of F. So if you have the three terms here, you've got the X, and that has to be in the domain of G. And so that means that you have some g of x over here. And that g of x has to be in the domain of f. So that you can then take that and apply it over here and get f of g of x. So if along the way one of those functions violates the domain, you divide by 0 or you have a square root of a negative number, then you're going to be in trouble. So let's look at an example where we have these two functions. Find the domain of those. So we've got f, which is 5 over x minus 1, of g of x. And we can do that. F is 5 over something minus 1. And what's that something that you plug in? It's g of x. So we get then equals 5 over something minus 1. And g of x is 4 over 3x minus 2. So if 3x minus 2 equals 0, it's not in the domain of x, of g. And so that would be when 3x equals 2 or x equals 2/3. The other bad thing is when if 4 over 3x minus 2 minus 1 equals 0. If the denominator of the f function equals 0, then we're bad. Then it's not in the domain of the composition, f of g of x. And so you can solve what values of x would make the denominator of f bad equal to 0. So that would be 4 over 3x minus 2 equals 1, 4 equals 3x minus 2, 6 equals 3x, x equals 2. So if you did graph this composition, then your domain would be everything else. Two-thirds and 2. So that's going to be negative infinity to 2/3, union 2/3 to 2, union everything bigger than 2. Right? So you can find, you have to check the values that you can't plug into the first function, and also the values that are going to make the outside function bad. So I wanted to give one counterintuitive example that helps a little bit too. Consider the function that's the reciprocal function, 1 over x. So I plug in, so f of x equals 1 over x, f of 3 is 1/3, f of 2 equals 1/2, like that. I can do the composition of f with itself. That just means you start with x, you take the reciprocal, and then you plug that again into the reciprocal function. So that's the reciprocal of the reciprocal. So that's going to be f of 1 over x, and then I take the reciprocal of that, and I get 1 over x. And if you simplify that, that's just x, right? If you do f of 1/4 or 1/3, I'm going to get f of 3 over 1, and then f of that is 1/3. So each time I take a reciprocal, if I do it a second time, I get back to where I started. If I start with x, I end up with x here. So you might think the domain equals all real numbers, because it's just the function y equals x. But there's a problem. What happens with 0? Then that's going to be, let me back up and do this. What happens if I plug in 0? Then I get f of 1 over 0. And you might be tempted to think that that's that, because you're just flipping, and that's 0. But this you can't do. 0 is not in the domain of the inverse of the inside function. So the domain of the composition of f of x is everything but 0. So negative infinity to 0, union 0 to infinity, if you want to write it that way. So it's summarizing what I'm saying here. Composition of function is just take one function, get an output, and that output goes into a second function. You can think about taking that second function and plugging it into the first function, taking the inside function and plugging it into the outside function. And that's great. There's lots of contexts where that works, and we'll talk about those. The one question I wanted to talk about was the domain of that. You also have to check that in the intermediate step, you're still valid. So in this example with the reciprocal function, the intermediate step is undefined, and so you can't, that's not in the domain. So just be aware that there are some nuances, some trickery with the domains of composition functions. Even if they simplify to something nice, they might have messed up along the way. So I hope this helps explain some ideas. We will talk about more in class and spend more time tomorrow going over examples.